All right, so I'd like to start again with the safety. Safety first, we always say, and as my colleague Yadvendra said, so one of the safety is psychological safety. And if any question you have, anything in your mind, please do not hesitate to ask, maybe after this session, or you can connect me later on as well. So let's move on. So this is the agenda for today. So I'll introduce to our R&D center that is in Pune. And yes, I do a lot of fellow investigation. I work with you guys. And then, we'll discuss how we do the fellow investigation. And then there are several case studies from heat exchanger failures. I'll be talking about that as well, different grades. And I'll also talking about the quality. So quality, I think in the last panel discussion, so a lot of talk about the quality. I think that really matters, and especially in the pharma segment. Then material selection, so I'll touch upon that. My colleague in the next presentation, he'll talk about the material selection, different grades that we have, that we are offering, and then we'll have question and answer. All right, so this is already presented, but I think what is very important here is that, so we are the R&D driven companies. So like, that's a very old, but at the same time, always in the market, we launch new grades. And thanks to you guys, in fact, you are the inspiration. You always comes with a problem. And then we try to understand, okay, where's the gap? And then we try to give the solution. And then we comes up with the new product. And that's how we grow. And we offer new solutions. So. And then there is not a single segment, Yadvendra already said that we are not catering to. So you name it and we are there. So then I'd like to mention that out of the 5 R&D, so we have 1 R&D in India that is in Pune. And I invite you to visit that. So this is the Pune R&D. This is the front side of our building in Pune. And here we are not very big by numbers, but we are very, very multidisciplinary. So we have people, we have discipline like materials, mechanical, chemicals, electronics, software engineers, so 16 full-time employee, and then we are growing. So then advantage of multidisciplinary is that we can think in different dimensions. And that is something very important. So someone was talking about the digital twin, so AI, ML. So that is something very much important. Then out of the several facilities that we have, so something very important that we call it workhorse of our lab is the scanning electron microscope. So then one facility, then it can do many information. I'd like to apologize here. I'll go a bit technical here, but I think that is very, very important. And I'll try to keep it simple. So then you are using metallurgy in your day-to-day activities. You have heat exchangers, and then you are using different grades. And then whenever you have failures, so like you come to us, so I'm talking about the different customers that we are serving, and then what we do, in fact, we take a small sample out of that, and we prepare that, and then we put this in the electron microscope. So this electron microscope is very, very useful. So in that, what happens, basically, you have the accelerating voltage, and then your electron hits the sample, and then you have different kind of information. And these information are like, you have the chemistry of the material, and then these materials have different crystal structures. You may have FCC, that is austenitic, you may have BCC, all those. So, and then you can have you can come to know what are the different phases that exist, and if there is some defects in your grade, so that also you can understand using this scanning electron microscopy. You have, of course, the different detectors in that. So you have one that is very common is called EDS, energy dispersive spectroscopy. You have EBSD. So EBSD is electron backscatter diffraction that gives you, the crystallographic orientation, the phases in your material all. So these are some of the information that we can have from this electron microscopy. So the one that you are seeing, the two different color, is your duplex grid. And duplex grid is like having two different phases in that. So the one that you are seeing, the red color is BCC, that is ferrite, and the blue one is your FCC, that is austenite. And the advantage of duplex is that you can have high strength, and at the same time, you have high corrosion resistance. But sometimes the duplex that is in the market, so if the chemistry is not tuned very well, so the problem is that you'll have a variation in the chemistry in these two phases. And then it cannot perform, it will not perform as per expectation. So then you can measure the chemistry of these two different phases by doing this same EDS. And then you have a spectrum like this. And sometimes at the grain boundary, you have something that is called intermetallics. So that intermetallics, so that varies from grade to grade. So that is detrimental to your mechanical property, that reduces the corrosion resistance. So what is that intermetallics? That information also you can get from this SEM. Then someone I was talking about, he was talking about the leaching. So the leaching is something like one element is basically leaching out, so parting out from your alloys. So, so you can do elemental mapping. So if some phase or some element is removing from your MOC, material of construction, so that information also you can get. Then during the manufacturing, you do heat treatment sometimes to understand whether it's a fully recrystallized or not. And that is very, very important. If your material is very nicely recrystallized, then it will have right properties that you like to see. So whether it's a fully recrystallized or not, so that kind of information also you can get. And even your sample is, say fractured. So that can be different modes, say it's a fatigue failure or it's a brittle or ductile. So that kind of information also you can get. So one facility, like one size fits all kind of, so this is that kind of facility. And then you can use this to check your quality of your MOC, whether it's right or not, and it can also give you the failure trend. So yes, so we do a lot of failure investigation, and for that we are using this facility a lot. And this is how we do the failure investigation. So this is in a very simple way I put it. This is how we do. So whenever we have the samples from your application, what we receive, so then what the first thing we do, that we assign a case ID, and this is how you track your sample, and then we preserve that, like a report or something after this. So then the first thing that we start with the visual inspection that gives you, okay, where is the problem area, and then we take a samples from that, small samples from the bad location, from the good location, so that you'll have more data. And then the next what we do is that we prepare the sample. So sample preparation is very, very important. If you are not preparing, then you can consider that if you are reading a book, and if there is some ink on that, so then your information is not clear. So sample preparation is like that only. So then you should do it very nicely. There should not be a scratch, otherwise there will be misinformation. And then we take those samples for light optical microscopy, stereo microscope, scanning electron microscope, and the data from this analysis that we put it together. Sometimes we send samples to the external lab. Here, Paresh sir is there. So we send to lab like TCR. And then one very, very important in-house tool we have. So now we have AI-based internal tool. So I'll talk about that. So we are also using that, and we put all data together, and then we present to customers. So when you discuss with them, then you'll have like more information, and then we keep all the information together, and then we put into the report. So then we recommend some grade also, and then what will be the cost effective and the best grade that can give you the better life. All right, so then, yes, so this is like how we do, how we use this AI. That is very interesting thing is going on in our organization is that digitization. I think that is everywhere. And we are very old company. The advantage with what we have is that we have reports around like more than 60,000. And then we have a tool, we call it Alleima Guru. So that is based on all the 60,000 reports that we have. And then we have so much data, you can call it gold mines, actually. So then you can ask this tool, so I have so and so process, I'm using this grade, so what can be the challenges, or what do you think that what can be the right grade? And then probably this can help you in doing that. And we are using it a lot. So our Vice President, Executive Vice President Tom Erickson, he's in one of the conference. The photo that you can see, he's in Stockholm in front of so many customers talking about the Alleima Guru in Industry 4.0 conference. All right, so let's look into some of the failure investigation. So then the one that I'd like to bring it to you, the ERW tube. So this is the welded tube, and there is some weak points in the welded tubes. We'll talk about that. So this is how the tubes are produced for the heat exchanger. So these are like ERD tubes, welded tubes. So where you basically take a sheet and then you round it and then you weld it. So that is the seam. So the one that you are seeing basically, so that is the seamed one. And then other process is called the seamless. So yeah, the one already touched upon that. So seamless, you have basically hot piercing technique that is generally used for bigger diameter. But for a smaller diameter, so what is very important or what we should have is the hot extrusion process. And we'll talk about, he already touched upon the difference between the hot piercing and the hot extrusion. So let's see, so what go wrong when you have the ERW tube. So I have very first example, when ERW tube was used in one of the wastewater evaporator. And here you had chloride in the media. And this was 316 Ti. In the morning, I was talking to someone, and then they have the similar grade. So whenever you have the welded tube, so you could see, like the corrosion. So though you can see that some funny face here. So sometimes you see something like this also. So this is on the OD side. This is how it was looking. And from the ID side, inner surface, you can see that there is a seam, and then on that seam you have some crack also, and then you can see some groove feature also. So whenever you have groove feature, so that is something sign of erosion. So your material basically is removing out. And then you have a lot of pit mark was also there. And then wherever there was crack, so we took a cross-section, transverse section, and then what we could see is that there's a big pit in the welded area. So whenever you do welding, so then you have like fusion zone. Next to that, you have heat affected zone. And that heat affected zone is basically having the lower temperature. And if you have stainless steel, so that has their own challenge. We'll talk about that. So we could see that most of the pitting occurred in the heat affected zone. But of course, like here we can see that that was also in the fusion zone. Let's look into the microstructure of this in the heat affected zone and fusion zone. So you can see that there's a variation in the microstructure in this. So that suggests that there is some temperature gradient. So if you go from fusion zone to heat affected, then base metal, so you have temperature gradient. So towards base metal, your temperature, like when you go from the from your fusion zone to heat affected zone, temperature varies from 4 to 800. And in that region, so there's a chances of the intermetallic phase formation. So then we use this EDS that I have shown you. So what are the phase that is forming? So you can see that in the left-hand side, you have something bright phase that you could see at the grain boundary. So that bright phase is the intermetallic generally we call, and then vary from grade to grade. So there you have basically the chromium and molybdenum. So those are very, very important. That gives you the corrosion resistance. And then you have segregation of those phases at the grain boundary. So what actually may happen is that then overall your chromium and molybdenum percentage will reduce in the alloy, and your corrosion resistance will decrease. So that is the harmful effect of this intermetallic phase formation. And then on the right-hand side, you have the chromium carbide that is forming at the grain boundary. And those chromium carbide, if it is there, so that is called basically the sensitization in your material that is in heat affected zone. So sensitization means if you have chromium carbide, and then in the vicinity of that, so you have depleted zone. And then that is prone to the intergranular attack kind of. You can see that there's an intergranular attack. And then this is the schematic. How, if you have some, say, sigma phase that is intermetallics, so then what happens that your passive layer that basically protects or that gives the corrosion resistance to stainless steel, so that weakens. And then if you have chloride in the media, so the one that is the weaker region, so that get attacked by the chloride and by, of course, this electrochemical process. And then your pitting, so the pitting is a small corrosion pit kind of feature it form, and then it grows, and then you have leakages. So then the term that you will hear a lot is PREN, pitting resistance equivalent number. So then what will happen if such phases are there? So your PRDN number will reduce locally. And in general, higher is the PRDN number, better is the corrosion resistance. That is one way you can say, like based on the year number, you also select the grade, but that is crude way, not the exact way. But in general, higher is the PRDN number, better is the corrosion resistance. So good. So yeah, so summary of that is that this ERW tube, so you will have to be very careful if you are using it. So there is a chance that you may have all those intermetallics form in the heat effect zone exactly happened here. Then let's look into the second example where titanium was used, and here also it was ERW, so it was welded. And you could see the condition of this. So this was in chemical segment, soda ash plant. And you could see how badly these tubes are. So you have the scales on that. And seeing itself, you can see that, okay, it's a very brittle, very thinning and embrittlement, right? So why it happened, let's look into. So then again, as usual, we do the same analysis, and then we take a small section, and then we look into under the microscope. So then what we can see that there's a thick scale that is forming, so that is titanium oxide. And then in the cross section, the microstructure, if you know titanium, so this is very unusual microstructure. You don't expect that. Then again, it's not very clear, so there's another technique we discussed. So that is EBSD. So you get the colorful image, and you could see that. So these two case kind of feature, the layer kind of feature that you are seeing from both the side. So those are basically alpha case, we call it, and then and in the center, you have lamellar kind of morphology. Ideally, you should have that equiax kind of microstructure, but what you are seeing is the lamellar kind of. I worked in titanium a lot, so I know. So this is generally when you have, when it is exposed to high temperature, and when you are cooling it, so then you have this kind of microstructure. And when we talk to customer that, okay, has it exposed to high temperature? Customer agreed, yes, there was a fire accident actually in this plant. So then this is like, I wanted to make a point like why this material selection is very, very important. What went wrong, I don't know, but this is a safety concern. So then, yes, so these were two examples where ERW tube, so there's some weak points in that, and better to go with the seamless. But it is not like if it is seamless and then it will not fail. No, that is not the case. Seamless do have the problem, though it's better than your ERW, but do have the problem if your quality of the tube, and when you are talking about the quality, so it's metallurgy, and it's also related to your processes. So if that is not good, and let's look into a few examples. So this is, you may be familiar because this is from your pharma segment only. This is the mechanical vapor recompression. And then here you have a feed, and then you have chamber, and then you basically, that is exposed to high temperature, and then your feed, so that converted to vapor, and then you have concentrate, so you collect that, and it again go into your system. You have a high compressor, and then that is basically on work on a Boyle's law, so you have a high pressure, and then that gives you high temperature, and then again you reuse. So then here the material of construction was 2205 duplex, so that we talk about, and let's look into this. So this is the parameter. So the feed parameter, you have chloride, sulfates, carbonates, all those were there. And then, yes, this is how it felt. So on the OD side, you could see some discoloration, but there were problems mainly from the ID side. So you had basically the localized corrosion. And let's look into the phases. What are the different phases it has? So it was duplex, as I said. So it's a two-phase austenite and ferrite. It was 50-50% of austenite and ferrite. So that was perfectly all right. But the problem here is that, so the two-phase, so I told you like you can have information. So you can do, you can have EDS analysis where you basically have information from the two phases, so 138, 139, and 139, if you see the chemistry, so that is having higher nickel, and chromium is less, moly is less, so you'll have lesser PRDN. And on the other hand, 138, that is ferrite phase, so here you have less nickel, but high chrome, high moly, and you have high PRDN number. So there is a, due to difference in chemistry, so there is a difference in the PRDN number, and if there is a difference in PRDN number, and if there is some aggressive environment, the one with the lesser PRDN number will get attacked first. And what you could see here, in this region, so the red is there, it means austenite is gone, that was expected. But there is something wrong in that region. So where we were expecting austenite will leach out, but here the ferrite basically gone. So this was also like, we couldn't understand properly what went wrong here. We refer literature, and then if you have, imbalance in the chemistry, so something like this can happen. So then we are still investigating this. So then what we have suggested, probably this is not the right grade for this, and then you should upgrade the metallurgy. So we have like a better grade. You can go with the, say, hyper duplex. So that is having better corrosion resistance, better higher PRDN number. And at the same time, you should have, so we have such a balanced tuned metallurgy, we call it, so that despite of the different phases, your PRDN number is the same. So we should have that kind of metallurgy, despite the difference in the phases. And yes, so this is another example. This was alloy 600. So alloy 600 is really good material. And this is also for pharma segment. This is used in pharma segment. Temperature-wise, not much, but we could see failure in this. So this failure was something not expected because metallurgy-wise, material-wise, microstructure-wise, everything was fine. But you could still see there is some localized corrosion on the OD side. So seeing that, you can see that, so mostly from the OD side. So in the heat exchanger, basically you have baffle, and then if there is something wrong, like if there is some wear between the tube and the baffle, so maybe due to vibration, or if there is a tolerance is not perfect, so you can have wear. And then we could see some localized attack also. You had chloride, and then like you may have initially wear, and then that gives you some narrow region where you have aggressive media, and that is called basically the crevice corrosion. So probably this was the crevice corrosion. So there are articles in the literature. So they have also seen the similar crevice corrosion when they have used alloy 625. Yes, we can again improve the metallurgy, or we can look into the design. So how we can stop that. All right, so this was again very, very interesting and very relevant. So there was a customer in the pharma, and what they complained is that they had moly leaching in alloy C276. This is the Hestaloy, and then this is known for very high PREN number. So Hestaloy is a very good material actually, and you should not have such a problem. And then this was really, like your entire batch was getting bad. So despite of the very good grade, high-end grade, you may have problem if your quality is not good. So when we look into the material, so what we could see that there was some intermetallics was forming at the grain boundary. So this is basically related to your heat treatment issue. So when your heat treatment is not right, so this can be the problem. Okay, so let's move to a few more examples. So this is my favorite. So though it was not from pharma, this was from chemical segment. And here, if you see the temperature, well, it's a very high temperature. The inlet side was 500 degree inlet, and the outlet was 55 degrees centigrade. And then here the grade was 321. So it doesn't have moly. And if you don't have moly, then your PRDN number will be further less down, 20. It has 19. So like if it had been come to us initially, so we could have easily told like this will not work. But customer faced a serious issue with this, and they wanted this sample to be investigated, and then there was a pitting, and then when we look into the metallurgy of this, so there were other phase. So this was basically austenite phase, and then we could see other phase in that was ferrite phase. So your heat treatment, of course, was not good. But now the question is that if it would have been the right quality, will it have worked? Probably not, because you have chloride also in this process, and then at the same time, if you look in the temperature, so that is on much higher side. So we have done the CFD analysis. So that is a computer simulation where you can have, you can basically predict the temperature, the real temperature based on the actual condition what you have. And then if you could see that the CFD model, so your temperature is around 200, and then of course this austenitic grade having the low PREN number will not work. And then here again we recommended the higher metallurgy. And then customer accepted that, and now it's more than 3 years, and then it's working nicely. All right, so then this is probably the last case, and then this is from the refineries. And here, again, I'd like to touch upon the quality, how important is the quality. So here it was super duplex non-Alleima grade, of course. And what we can see here, then, so it failed just within 2 months. Why? because you had something like intermetallic phase that we talk about, the sigma phase, and then you have nitrides. So you have, whenever you have nitrides like chromium nitride or sigma phase, so the term that is called CPT, critical pitting resistance temperature, so that will come down, and that is started failing just at room temperature. So then here, grade was right, seeing the temperature, so super duplex should work here. But due to this problem, so here basically the heat treatment was the issue, so this didn't work. All right, let me just now quickly look into or just explain what can be the quality issue. So here I have some examples where you have the same grade, TP316, and from different manufacturers. So same grade from different manufacturers, what can go wrong? So then ASTM standard says that you have some specs. So if you are talking about the nickel, so it should be between 10 to 14%, and then it is up to the manufacturer how much they want to keep. Similarly, you have chrome, moly, so they optimize sometimes based on the property they want to achieve. So the same grade, and you see the difference in the microstructure. The tube A that you are seeing, it's a very coarse grain microstructure. So if you have coarser grain, so basically your strength will come down. The second one that you could see, so there is a ID side. So still I have sample outside. So still I have sample outside, and we can see that there is a ID side, there is an attack, and then the third manufacturer, you can see that tube C. So there you have the stringers of bright phase. And then the fourth one, you could see that there is a melting from the OD side, and that is R grade. So, your process is very important. And the morning first half, so Yadwen talked about this different hot working processes. So how it can affect the quality. So as he said, so you have, in the melt, you have most of the defects in the center, and you need to remove those defects when you are when you are doing the hot extrusion. So that gives basically the higher quality. So let me finish. So you have problem. In fact, I talked to some of you, and then you said that, yes, in graphite, you have a lot of failure despite a very good heat transfer. And then, of course, this is also not the solution. So, in fact, so this is the key takeaways I would like to say. So, ERW, those are having the weak points. Not good idea to go ahead. You should choose seamless, of course. And the second point I'd like to make, even if there is the grade is correct, MOC is correct, you should focus on the quality.